Okay, so this is going to be on the fractional Calderon problem. So previously in the first talk, so Venki talked about the Calderon problem. So in this talk, so so I'll be talking about the fractional Calderon problem. So first of all, uh, what does it mean by this fractional Calderon problem that I'll introduce? And so basically you can have the idea that it's about the fractional operators and then some Calderon type problem or the inverse problem that we're going to solve. Okay, so I start with recalling the Calderon problem. So but basically Venki did it in one slide. And then we'll get into the detailed plan that I'm trying to cover in the two talks. So mostly in the first talk, I'll talk about the forward problem or the direct problem. As I can see that that's the only topic I'm covering. And then in the next part, probably I'll talk about the inverse part or the let's see how it goes. So okay, so let's recall the Calderon problem again. So we have that the conductivity equations as we have seen before. So we have a bounded domain omega in Rn. I mean, not being bounded also, like it could be a slab or something. You can allow unbounded domain as well. And so this is the second order elliptic equation. So gamma is the represent the conductivity of the equation of the domain omega. And then, so you measure the static voltage and the current at the boundary. So that forms the Cauchy data. And so this is represented on the boundary. You can see that this is the Dirichlet data and this is the Neumann data. So if you plug the voltage or the either way, the current, then you measure the other one. So if you plug the Dirichlet data, so you measure the Neumann data as current. And as a whole, we call this is voltage current measurement on the boundary. That's basically the Cauchy data. So now the question is that, so you're measuring something on the boundary and then you want to detect the conductivity in the interior or even in the whole domain omega bar. So this is the problem. So given C omega, so that means the Cauchy data. So you'd like to determine the conductivity gamma in whole omega bar. So this is the kind of inverse problem we talk about. As you have seen in the previous talk, that the forward problem means that you already know the gamma, you have the source, I mean, as the Dirichlet data or the Neumann data. So you solve the problems automatically. The other part of the Cauchy tree is determined. Now here you presumably don't know what is gamma, so you know that there is some gamma, and that you want to determine just measuring the Gaussian. That's the way we say that's inverse problem, and it's formulated by the Calderon, so it's known as the Calderon problem. And we know the result. So if the gamma is the isotropic matrix or it's a scalar function, of course it's positive and so on. So then so there are three cases I just want to mention. Just one case is not here. So for n equals to 1, it fails. So in one dimension, you cannot do anything. So basically, you have very less information. So you have just 2 points, and on the points, you have just 4 data. And from there, you cannot track anything about the interval. So where gamma is defined over a one-dimensional interval. So in one dimension, it fails. Now in two and higher dimension, it can be solved, and you can show that if it is isotropic, then you can identify uniquely. Of course, the regularity is a point of discussion because this problem is kind of very much interconnected with the UCP, that's the unique continuation principle. There are two school of thoughts that one could believe that this is very much connected with the UCP. So the regularity, what you can do, I mean, where you can solve the inverse problem, mostly that is where the UCP is true. That means the unique continuation for this particular operator. the second order operator. And that has been done, at least for 2 dimension and 3 dimension and so on, 3, 4 also. But higher than 4, still there is a problem, even that could not achieve. But nonetheless, in the physical dimension, it's solved. But below that level, for instance, that W1N is the optimal regularity, we know that if you want to go below W1N, then still it's not solved or not known. But this problem is posed for just L infinity data. So for 2 dimension, it is known. For 3 and higher dimension, it's still not known. However, if you consider the anisotropic matrix, so that means it depends on the directions. So if you are in n dimension, then it depends on n dimension. So then the unique recovery fails. So then there are 2 parts. So this part is not actually covered in the first talk probably. So I just want to touch on that. So first of all, if you have an anisotropic matrix, then you cannot expect to recover the whole gamma. There is a problem. You can show that there is a gauge invariance. So you can cook up certain diffeomorphism, which is constant on, or which is identity on the boundary. And for those diffeomorphism, you can actually show that the 2 different metric or 2 different matrix has the same DN map. So you cannot hope for recovery. Now the question is that that observation is due to the Luke Tatar, very well-known name actually in homogenization. So it was my previous topic. And then the question is that whether that's the only obstruction to recover gamma. And that part is not solved. That is solved only in 2 dimension. You can prove that in 2 dimension, that's the only obstruction. The only obstruction means that only the change of variable is the obstruction. And so you can recover up to a change of variable. But 3 and higher, still there is a problem. And then you need much more regularity that even reaniticity and so on to tackle in 3 and higher dimension, where in 2 dimension, you can actually do it for L infinity. So in 2 and 3 dimension, things differs a lot, at least in the Calderon problem. So I'm just saying all those things, but we'll try to compare all these facts when I'll talk about the non-local Calderon problem. And we'll try to see that whether we achieve a little bit more or less and so on. Okay, so with this, so we will get into the fractional Calderon problem. So I just want to tell you the problem first, or the kind of idea that the problem carries, and then we'll get into that because you can formulate in many ways. Even in the first talk, you have seen that instead of this equation, that conductivity equation, so it was reduced into the Schrodinger equation. So that means you have the leading order term as the Laplacian, and then you have some zeroth order perturbation, and also at the end, the magnetic Schrodinger equation is discussed. So it's kind of the leading order term still remains as the Laplacian. Then you have first order perturbations and zeroth order perturbation. So of course, you can talk about those problems in fractional Calderon problem, but I just want to tell you about this particular problem, and then we'll get into that. So this is kind of the very analogous thing of the Calderon problem.
Yeah, very good morning. Am I audible?
Sorry? I didn't understand. What's your question?
Yes, sir.
Yes.
Okay, so are you able to see the screen also?
Yes, sir.
Okay, thank you. So in the last session, we have dealt with surface area, means like how to evaluate the surface area for a given surface. And we have also seen the surface integral of a vector field. And also, we have seen how to parameterize the.
Is this question related to this problem, or I don't understand?
Seems by mistake someone played some other video.
Maybe you can proceed now. Like,
Okay.
Yeah, I muted that person, so you can proceed.
Okay. Anyway, so as I was talking about, so this is the analogous fractional Calderon problem. So you can see the change here, that what I did in at the operator level. So here you can see that there was no power, and the change what I made here is that at the operator level I put some a, and so this is a non-local equation. Of course, I have to explain what is non-local equation. And then the question is that you do this similar kind of measurement, but now not on the boundary, but instead of boundary, you do the measurement in the exterior domain, and that is something related to the non-local equation, that the non-locality it somehow forces you to go to in the exterior domain, because to define the operator earlier here, so everything was defined in a bounded domain, or in some open set omega. But now, if you want to talk about the non-local operator in general, so then you need to define in full space. So things are defined in full space, and then it satisfies some equation in some domain. Um, for example, here it's omega, and then so leaving the domain, so whatever is left, that's kind of the exterior domain, and there you try to do all sorts of measurements, and then you figure it out that what is gamma in inside. So that's the essential idea, that generalizing the analogous Calderon problem for the non-local equations of the fractional Calderon problem. But that's not all. Even for the non-local equation, you can, so the first big change what I can see, that the Cauchy data, it's a non-local Cauchy data, and it's defined over this omega e cross omega e. So that means, so it is defined on some n-dimensional domains, or n-dimensional object you can think, so n cross n. So if you think in that perspective, it's kind of the 2n count of variable. But whereas in this case, the Cauchy data was defined over the boundary. So this was kind of n minus 1 dimension, and this is n minus 1 dimension. So you had this count of 2n minus 2. So this is a big change. So you gain kind of two more information. So anyway, so that's one thing. And then we ask the same problem. So let's say you have this non-local Cauchy data in some exterior domain, and then is it enough to determine gamma in omega bar? So that's the formal questions of this Calderon problem. And then we ask the very similar questions, that we know the right answer for a equals to 1, that if gamma is isotropic, then at least in this case, we expect unique determination. And if gamma is anisotropic, then do we expect some non-uniqueness? Or as I said, that you have a little bit more information, or it seems to have a little bit more information. So then can you actually recover the anisotropic gamma? So these are two questions. And additionally, I want to add the third questions that I mentioned just before when I was discussing the Calderon problem, that for n equals to 1 dimension, it fails. So you can ask that n equals to 1 dimension here, because now you're not dealing with the points, you're dealing with some other intervals. So you have little more information, and at least for n equals to 1 dimension, is it true or not? So we'll get into those questions, and we'll see whether we can answer some of them. But now we have to really talk about that. What does it mean by this, the eighth power of this operator, and how it is defined, where it is defined, and the relevant Sobolev spaces. And as I told you, that probably I'll spend some time on the direct problem, and since I have much more time, and then I'll get into the inverse problem. So let's begin with the fractional Laplacian. So the simplest possible way you can define, or it's the well-known method, the way we define the fractional Laplacians, that's via the Fourier's transformation. So basically, so you have this operator, so which is a constant coefficient operator, Laplacian. So you know that if you consider in Rn, the plane waves are the the eigenvector, and then it has this continuous spectrum, and the continuous spectrum is nothing but just mod c squared. So if you want to define that some operator to the power a, so it has to be like that you take the spectrum of that Laplacian or that operator L, and then you take the power to define the L to the power a, the or fractional Laplacian minus Laplacian to the power a. So basically, you take that that particular power of that continuous spectrum, and then you superimpose with respect to the eigenvector. In this case, it's a plane wave. So you can define that particular operator. So, and in this case, it looks very simple because you can write everything in terms of the Fourier transform, because to define the Fourier transform, we basically use the plane wave that e to the power ix dot c. And so let's say if you have a, but it's not that useful. That's my, if you think in that way, of course you can define, as I was trying to explain you, that via the spectrum, you can define any other operator, because it's essentially a pseudo differential operator. So you have to formally go through the symbol calculus and define through it. So if it's a constant coefficient, then you're kind of lucky in this case. That's the message I just wanted to give. And of course, you can invert it. So because you know the Fourier transform of this quantity, you can write it down explicitly. So so from the Fourier space to physical space, you can have some integral representation, and that integral representation is given by this object. It's kind of simple, that ux minus uy by x minus y to the power n plus 2a. And so you can see that x equals to y, it has the singularity. So you have to take the principal value, or that means like you subtract a ball of radius epsilon around x, and then you do the integral, and then you take the limit, and everything makes sense. Then you have that quantity, which is known as the fractional Laplacian of u acting on some point x. And from the definition, you can clearly see that even if I want to compute at one single point, that I need to know the value of u everywhere in Rn, because you can see that it's ux minus uy, so ux is fixed, that's okay, understandable. But this uy guy is traveling around the whole Rn. So that's the way you get the sense of the non-locality, that the problem is that even to compute, to know at single point, that you need to know it everywhere, that's the whole Rn. And so that's the thing I was telling when I was introducing that the fractional Calderon problem, that instead of boundary data, so why do you need to measure the exterior domain? Now, because it's already defined there, and you have to take care of that, otherwise you cannot make sense of that problem. And the second thing is that, which is not clearly visible from here though, so that it doesn't preserve the support. It says that suppose if you take a C-infinity function, so now outside the support u is 0. So of course, if you take any local operator, for instance, it's Laplacian, so Laplacian u is also 0. But here in this case, if you take that u is a C-infinity function, and if you just want to compute that minus a plus aux outside the support of u, then it's not 0. And we'll find something more interesting, actually the interesting fact, I would say, that if it turns out that is 0, that outside the support of u, the fractional Laplacian is 0, then zero is the only option. So that's the only zero function can satisfy both of these conditions. So that's kind of the strong uniqueness property, or it's a very strong unique continuation property that you have, that it has this very strong infinite speed of propagation. So if something is non-zero somewhere, so through this integral, it will propagate throughout the whole domain to make it non-zero everywhere. So that's the kind of idea we have. And I just want to tell you a couple of things here so that's one kind of fractional Laplacian we can see here. That's the most common that's in Rn. There are various fractional Laplacians which floats around the, in literature you can find a lot of this. For instance, that one of the possible thing we can talk about, just I was explaining before that via the spectral. So if you consider the Laplace operator, if you consider the eigenvalue problem in particular in a ball, or in a finite domain, or it's a nice problem. So you can deal everything. You can apply this compact operator stuff, and you can have the discrete spectrum, and it goes to zero. So this lambda 1, lambda 2, lambda 3, lambda n, and so on and so forth, and phi1, phi2, phi3, so on. And with that, so then taking power of those the eigenvalue, and then you superimpose with those eigenvectors. So then by that way also you can define the fractional Laplacian, but that fractional Laplacian is not the spectral fractional Laplacian, or that is different, that depends on omega very much, and which is completely different from the kind of fractional Laplacian here I'm talking about. So this is very global. It is defined throughout the Rn, and it has nothing to do, or it has no sensitivity with any particular domain. And the second thing that I'll also introduce, it's kind of another zero differential operator, so that it depends on the omega, not in that spectral sense, but it's something known as that regional fractional Laplacian. So here, as I said, it is the whole region that are in, but the regional fractional Laplacian, so it comes with the notations of minus plus omega to the power a. I'll introduce it later, but I just wanted to tell you that instead of doing the integration in Rn, so you do the integration over omega, and that's the definition. So you can just write any like similarly people defined, let's say if you have even any manifold, or in certain spaces, it need not be Rn, but you can replace with any other domain, and of course that integral very much depends on that domain, and whatever you get, you call that the regional fractional Laplacian, and so on and so forth. Anyway, but those kind of definition you cannot recover from the Fourier transform. So here you can recover this definition. You can show that these two are equivalent. But then there are many ways you can define the fractional Laplacian. The thing what I like, or that what I found which is more useful, or kind of useful for my purpose, that's if you go via the heat equation. But before getting into that, so I just want to mention one particular fact here about this constant, the CNA, that appears here, depends on n and a, but it has this kind of asymptotes, that a into 1 minus a. So if you want to go to either way, it's 0 or 1, so it goes to 0. So it's not so easy to see that if you just pass to the limit, a tends to 0 or a tends to 1, that this will give you the plus u or the u. It does, but it's not so simple to just visualize it from this integral part, because of this constant. The behavior of the constant it's not tells you that this goes to 0, so that means that as a tends to in particular 0 1, so it has to go to infinity, so that the 0 times infinity can give you something meaningful here. So that's that's the purpose, and that's the reason I just mentioned about the role of this constant and what happens if you make this kind of a tends to 0 and 1 in this integral. So it is going to blow up. So that's the thing. But the constant will take care of that, and ultimately you will get a good thing. Anyway, so the next thing what I was uh, yes was telling you that so you can define this fractional Laplacian via the heat equation and or the heat semigroup, and then I find that it's very useful and it's kind of very friendly to work with. There is of course another way, not through the parabolic equations or the heat equation, that's through the elliptic equation you can define. So that we'll do. That's kind of the very famous work of this Gaffrey Sylvester. So you consider elliptic equation, but it's not purely elliptic. It's kind of the degenerate elliptic equations. But you solve the elliptic equations and then you consider the DN map. And from the DN map, you can recover the fractional Laplacian. So I'll talk about that later. But here, it's not the elliptic equation, but it's just the heat equation. This is also a very natural way you can define that. You simply consider the heat equation and uh, with the initial data that, or the Cauchy problem at t equals to 0 with this u. And if you just define this formula that uxt minus ux, and then you divide by t to the power 1 plus a, and then you integrate over the time, then you get back the fractional Laplacian of u of that means at this function and at this point. And from the knowledge of heat equation that we know it has this property that the infinite speed of propagation, right? That's the thing I was mentioning, which is similar to elliptic case, but very different from the hyperbolic case that where you have this finite speed of propagation. So if even if is, u is 0, let's say u is compactly supported, so outside a compact supports it, the small u is 0. But when you solve the heat equations so that this u this capital U, it is non-zero everywhere. And moreover, as you know that you can write down the fundamental solution very explicitly. That's going to be the e to the power minus small x squared by 4t, and then you have 1 by t to the power n by 2, and so on and so forth. And the point is that that's the analytic function. So you can get, of course, from the semigroup theory, you get the analyticity with respect to time. And as in particular dealing with this Laplacian operator, you get it's a constant coefficient case. So you get the uh, analyticity with respect to x. So both with respect to time and space, you have this analyticity and so on and so forth. So the analytic function cannot be 0 on an open set. If it is, then it has to be 0 everywhere. So even it can't be 0 on a measurable set, positive measurable set. So yeah, so the point is that it's, of course, it's non-local and it doesn't preserve the support. And as I was telling you that even to calculate at one single point x, that you need to know about u far away from x. And that also you can see it from here that you need the inter t line just to compute the fractional Laplacian. So that's essentially the idea of the non-locality I was trying to tell you, or to give you, that what very much differs from the local operators, where you do everything around a point, around a neighborhood pair. But here it is not. It depends on the region where you are working. And in the simple case, we are dealing everything in Rn. But if you want to do fancy stuff, I think in manifold and so on and so forth, but the story is same. Okay, and so one of the advantage of this particular definition through these heat equations, you can define for any general operator. So that's the thing. So this is one kind of general operator, if you remember. This is not some Laplacian to the power a. So this gamma is inside. So it's kind of divergence gamma grad. It's a second order operator, though it doesn't have first order, zeroth order term, but still it's not just Laplacian. Anyway, so in particular, you can take any self-adjoint positive definite operator in Rn. So here you can see that it has the second order term with this matrix AJK. It has this first order term uh, just to have this symmetricity, the self-adjointness. So you need to write it in this way. And this I is this complex number, and then you have the zeroth order term. So that's the most general second order operator you can think of if it is self-adjoint and so on. So then, as I said, that you can consider the heat flow with respect to this operator or the heat semigroup. That means solving this heat equation, and then you can use the same method to define this L to the power A ux. So that means the fractional power of L. And so that's going to be this uxt minus ux divided by t to the power 1 plus a. And where this capital U solves this parabolic equation. And so this is very much for a not equals to 1. So as I think I mentioned, oh, okay. So this definition is very much for a not equals to 1. I mean, if you put a equals to 1, so then there's a trouble. The trouble is that it becomes a t square. And as I was telling you that uxt is the analytic with respect to time. So if you try to expand with respect to time near 0, so that's kind of that ux0 will cancel out this ux term. And then you will have this t term with the derivative at 0, let's say. And then if we have this t square, so then t square will give you 1 by t, and which is not integrable near 0. But it is integrable near 0 when a is not equals to 1, or a is strictly less than 1 in particular. Then it will give you the similar calculation that 1 by t to the power a, and which is integrable. So that's why this definition makes sense to define the non-local operator in this way. But if you try to put a equals to 1 there, it doesn't work. It blows up. So that's the message. And if you want to define this LU, that's, as we know, that you can just simply integrate this U, this capital U. So then you can get the stationary equation. And at the stationary equation, you just, that means on the Rin, you can simply get the that LU is this L, this, if you call this integration of capital U some V, then you'll get this LV equals to U in Rn. But other than that, you can't do much about this. Anyway, so that's the idea of that how we define this operator. But of course, I didn't mention the spaces and so on and so forth. So we have to do that. But before that, probably I'll try to motivate that how this kind of operator appears in the the real problems, or why we should care about this kind of operator to solve these inverse problems and so on and so forth. That's one of the questions we have to understand. And as in the Calderon problem, which is very much related to the electric engineering problem, the static voltage current measurement. So let's see whether we have this kind of analogy or not. So this is the one thing you can see a lot in literature. Actually, at least it's there. I mean, I think a few decades ago also, like nowadays, it's very active field of consulting the different diffusion cases, like whether you have super diffusions, the sub diffusions, and you can see that where you are putting this A, it's very important, or you can have mix like, so this is the fraction with respect to space, but with respect to time, so it's not fractional, but you can have both. This is known as also the Caputo derivative because it's a one-dimensional thing. And then so this is very much useful so in understanding the diffusion process, which involves any long range interactions. So as you can see that this kind of operator kind of interprets uh, non-local phenomena or the interactions between one point to far away any point. So if you want to understand any diffusion process, most likely most of the diffusion process, and in particular any stable process, or the Levy process, or the population dynamics, financial one. So there are a lot, even in biology and then in physics. So it's this kind of diffusion equations. So it's the fractional diffusion equations, or in general they don't call the diffusion process, but they call the stochastic process. It's very much common. So we'll try to go through one of the examples. I will try to convince you at least one of the examples that I learned from the work of Valdonoci. So by the way, this I'm not referring any book, but these are the things you can get it. There are some pioneers. I think the Valdonoci is one of them. Enric Valdonoci. He has several books, write up, several papers. You can actually look at our paper, or at least whatever I have written. I try to be self-confident, but I'm not saying in that way. Um, but all the details you can get it there too. So anyway, so let's talk about one example of random walk. So so idea is that, so you have a probability distribution function, and so that's I'm denoting with this kappa. It's a large kappa. It's a function from R into R. It's an even function, and as usual, there's the integration has to be one. And here it's a discrete case. It's a random walk. So you are walking on the grid. The grid is given by the z. Sorry, it should be z to the power n, and the sum is 1. So that's the necessary condition. For instance, that like in the continuous case, one of the easiest way to think that e to the power minus x, some constant e to the power minus x square kind of functions, which is even, and you have this normal distribution, the integration is 1, and so on and so forth. So now what we'll do that you give me a small age, and then we'll consider the random walk on the lattice that is z to the power n. And this is the rule that, so this is with age with respect to the space, and then you need to give me any unit of time that I will scale the time that I'm calling the tau. And that might depend, and actually will depend on age. They are correlated. And so the point is that, so you have a particle, and this particle jumps from one point of the grid. It's somewhere in the grid, let's say it's to the brain, to another point in the grid. And the point is that, so it can jump fine, but then you want to associate some weight, and the weight in a sense that you want to associate the number, or the probability that, what is the probability that it can jump from this point A to point B, or point A to point C, and so on and so forth. And so that will be given by this kappa. So that's the reason I introduced this kappa at the beginning. So as I was telling you that this is exact formulation. So the probability for which a particle jumps from one point to another point, so that is given by, so you can represent those 2 points. So this is hk and hk tilde. So in k and k tilde is basically some points from Zn from the grid, and it's given by this kappa k minus k tilde, right? And as it is in this even function, so you can see that going from k to k tilde or coming back from k to k doesn't really matter. The probability is same. Now you can also see that I'm allowed to jump from any point to anywhere. So like it's the whole Zn in is kind of my territory. So I can jump, but as the total sum is 1, so the whatever the longest jump I make, so so a very small probability is going to assign with that. So that means that so if you are jumping, in a compact domain, or near about a point, so you have much more weight, or that means the probability, the weightage which is coming through this probability density functions, which is much more bigger. If you go further, of course, it's non-zero, but the contribution is small. And then, so from that rule, so if you somehow make this is continuous, or if you want to see it in a limiting case, that means that h tends to zero, or the time unit tau tends to zero, then do get something interesting. That's the asymptotic analysis we are interested in. And we'll see that. So that actually leads to the fractional Laplacians, or some kind of diffusion equation, or the fractional diffusion equations, or the stochastic process that I was talking about. So the long jump to the fractional Laplacian. So this is the idea. So you have, this is the function, this uxt. So it denotes the probability at some point x, and at some time instant that's t. And then you want to see that what is ux plus t plus tau. That's a little bit increment you did with respect to time. So that means you have to take care of the all possibilities with all possible positions that x plus hk, that they are waiting at the time t. And so that's a history you are looking for. And then they could be at x minus hk or x plus hk, and then they'll make the jump from x minus or plus hk to x, and that jump will take place. So and then you reach to this t plus tau point, right? So that means if you want to figure it out, the probability at x t plus tau, so basically you need to take the sum and the corresponding probability weightage with respect to all possible points. So if you do so, so you get back this simple formula, and then from there, as we'll be interested in, so what would be the increment, the rate of change, so that there comes the derivative if you do it in a continuous manner. So that means you subtract the uxt, divide by the tau, and we'll make tau tends to zero later. But if you do the same thing on the right hand side, so since the summation kappa k is 1, so you can subtract this object. This is independent of k, so this makes sense. And then while I'm dividing by tau, so I have this relationship with this h, the tau equals to h to the power 2a. So on the left hand side, I wrote tau, on the right hand side, I wrote h to the power 2a. Now, you want to consider this kappa functions, which is kind of explicit. And here I'm considering this kind of singular weight functions. You can take k0 equals to 0. Of course, it is at 0, it is not defined. But if you look at this definition, uh, like I started with, I said that it is defined everywhere in Rn. So, I mean, at that point, you can just simply assign 0, whatever. It doesn't really matter. Of course, you can take the smooth curves, or that's kind of e to the power minus y square, or e to the power minus y kind of things, which has no singularity, but that doesn't give you the interesting things probably. So here we are interested with the asymptotes when with the two relations that we made, one connection with tau and h, and another one that this probability density functions that we have chosen as that some singular weight functions, and in particular mod y to the power n plus 2a. And from there you can easily see the connection to the fractional Laplacians, because next what I'll do that I'll make tau tends to 0. So if you do so, so then you get back the continuous limit of discrete random walk. And on the left hand side, you get back the partial time derivative with respect to, of u with respect to time. And on the right hand side, you get back this quantity that ux plus y minus ux divided by mod y to the power n plus 2. But this is not the fractional Laplacian, but you can do a little bit algebra. So if you add 2 times, so, and if you change the plus y to minus y, since it is always even, so you can actually write it down this way. And then it gives you the fractional Laplacian. So as you can see that here, there is no singularity, because if you remember the definition that I introduced, maybe I should go back, then it would be easier to remember. Yeah, so you see that here I have this principal value thing, because that at x equals to y, it is not defined, so you need to subtract a ball and then you have to do such stuff. But if you use this translation, then you don't have the singularity, so you're kind of safe, because at y equals to yeah, so here you can see that at y equals to 0, so what happens? So the singularity cancels out in some sense. So you have yes, so you don't need to take care of this, you know, the principal value. You can just directly write down this integral. That integral makes sense, and it gives you this fraction of Laplacian. However, this is not, you can do it for this fractional Laplacian case, but like I said, if you have some L to the power A, where L is a second order differential operator, so then you can't do this kind of thing, uh, because it might depend. So this kernel K might depend on X and Y. And there could be several complications to do that. And that's a way actually you actually cook up a lot of possible, this Levy flight or the Levy operator or the continuous time random walk operators. So it's just that this function, this is it could depend on X and Y both. It can depend on the basis of region, that in one region it acts as some fractional Laplacian, in another region it acts as another fractional Laplacians, or in a non-trivial way. So it's basically you are dictating that how the particle should jump from one place to another place. And there are interesting examples that which appears in physics or biology. That's when you have the membranes. So it's there. So like it's kind of the porous medium kind of thing, that the particle can jump from one place to another place, another one domain to another domain. But the problem is that when it does that, it contributes almost to zero. I mean, it's nothing. Um, but it is allowed kind of thing, or it says that the particle kills themselves when they do that. Anyway, so that's one part, and then so if you make this limit equations, that means we get back these fractional diffusion equation. So that's written here. It's as partial du plus Laplace au equals to 0. And here I just wanted to tell you that you can try to find out the fundamental solutions just to understand just how this diffusion process works. And as it turns out that, as you know, that if you put A equals to 1 in the classical heat equation, so then you do get back that e to the power minus mod x square kind of thing. So it's a Schwarzschild functions, and you know that it has this infinite decay and so on and so forth, because the inverse Fourier transform also give you that e to the power minus x square. But here, if you have the fraction, then it's no more true. So then you get kind of the polynomial decay. So it is very much different. So you can see that the polynomial decay is kind of slower than the exponential decay. And so you can immediately see that how the diffusion process is controlled if you just put this A here. And I just also wanted to add here that even if you have some alpha here and A here, of course you can find this kind of fundamental solutions. you know the Fourier transform of the fundamental solution, but the inverse Fourier transform of those fundamental solutions, it's not easy. Even so, they are represented by this something called the Smitter reflect functions or something like that. It's kind of tricky, and even the reason I'm mentioning that, even to show that the fundamental solution is positive, it's not easy. In fact, there are examples that the fundamental solution could be negative depending on the kind of diffusion process, the stochastic process you are choosing. Okay, so so things can go a little bit, counterintuitive way. So that's the thing. I was trying to tell you when you try to invert this Fourier transform, because the Fourier transform of inverse Fourier transform of Fourier transform of positive function need not be positive, and then you have to take care of something called the Isaac-Sonnenberg theorem or something like that. So in order to make sense of it. Anyway, so now, so here in particular, we'll be talking about the stationary case. So that means that only the fractional Laplacian part. And I'll start with the fractional Schrodinger equation. So that's kind of the baby version. So as you can see that we have this fractional Laplacian operator, and we have a zeroth order partition. And we have some exterior value problem that u equals to f in omega e. So this is your domain omega. Q is defined here in omega. And in omega e, you have this Dirichlet value at the source. And then you want to solve the u in some suitable space. And you want to define what would be the Cauchy data and what would be the relevant, the inverse problem, so that from that information, you want to determine Q uniquely, or if you can't, then don't make case with appear. Okay, so this is the direct problem. So this is the first time I'm introducing the Sobolev spaces. So here we are going to solve. So my f is from hs omega e. I'll define it, and then I'm looking for a solution in hs of Rn. And now, so let's talk about this fractions Sobolev space. These things are, it's boring, but it's a bit crazy because like several authors use several notations and with several equivalent norms and so on. So maybe I thought we can go through once. So HR of Rn is very simple, that you take like basically all possible tempered distributions. It's to all of these Schwarz class functions. And then if you have this simple way to check, that's actually checking in the Fourier space, that 1 plus mod c square r by 2 you had. If it is in L2, then we call that collection as HR of Rn. This is the index R appears. And this is, you can use this definition for any real number R. And then you can assign the norm. It's basically the graph norm. So you have this L2 norm, and then you have kind of the fractional derivative norm here. This. So then you can do the similar stuff in the physical dimension, physical space, that's in X space. And so that's the kind of equivalent definition you can use. But here we are just taking the fractional powers. R belongs to 0, 1. If you want to do it, let's say 1.2, so first you have to define for 1, and then you have to define for 0.2. But like the previous definition automatically will take care of this 1.2, because it's a little bit different in that sense. So this is a very straightforward definitions, and where you can usually see the inner product space, and this is the inner product we have. And if you just put u equals to v, then you know that you can get back the norm. Okay, so then the question is that, okay, so what is HSO? So O is like any open set. So first we define for Rn, and now we're talking about any non-empty open set. And that need not be bounded, because I mean, it has to be unbounded, because as you see that this omega e is always unbounded. I mean, if you choose omega is bounded, or at least in picture it looks like it's bounded. So omega e is unbounded and has taken that AF is from hs of omega e. So it's kind of you have to take care of all possible non-end open. So that's very easy definition, that you take any hr of Rn functions, you restrict R in omega, and that's the way you define any hr of O functions. And of course, it's you can define the norm. It's this this is the national norm. You can give that you take all possible v such that the restriction is u, and then you minimize their norm, and then whatever you get, that you assign as the norm of the function of h0. Definitely, you can do it like the analogous way that we discussed before. So that's another way of defining HRO, that you take in L2 and then you take this ux minus ey, x minus y to the n plus 2 by r, and you ask for, okay, whether it is L2 of O cross O. And if it is, then you assign it as a HRO function. And then, of course, you can define this inner product space like before. And if you put u equals to v, you get back the term. Okay, so these are kind of known stuff, but we have to go through this. And then the important thing is about dual space, because essentially what we'll do, I just want to tell you why I'm talking about this, that so you see that the way we solve the inhomogeneous problem, that so basically we subtract and we make it 0, right? So we consider v as u minus f. So then I'll have v equals to 0. Somehow it will help me to define the bilinear form, like what we do in the local case, and to apply the Poincare theorem and so on and so forth. But that will give me some non-trivial, non-trivial right-hand side, and I have to make sure that whether the right-hand side belongs to the dual space of H minus S of Rn. Otherwise, I'm in trouble. So for that, we have to make sure that for the dual space and how it is defined, one of the easy thing, as you can expect, that if it is in Rn, so like Hr of Rn, then you stick star, then you get back H minus R of Rn. That's very simple. And now it's a little bit complicated as it comes, that when you want to do it for H's of O, and it's kind of counterintuitive in some sense. So there are two spaces. Just take a look, little careful manner, that so we are dealing with, so we have defined two spaces, that one is kind of common, that HRO 0 of O. So that means you take the all CC infinity functions defined in this open set O, and you take the closure of those CC infinity function. Now the question is that with respect to which norm? So we have already defined two norms. So one is HR of Rn and then HR of O. So if you do it with HR of O, you get back HR0O. That means the trace is 0. But if you do the same thing, that cis infinity O, the closure of cis infinity O, but with respect to HR of Rn norm, so then you get back something slightly different space. And that space is not same as this space. It depends that with what kind of O you are choosing, like what kind of open set you are dealing with. If it is not Lipschitz and so on and so forth, so then these two spaces are really different and can create a lot of nasty things. So one particular example that you can check, that, for instance, and especially this happens with this smaller value of R, that if you take, for instance, R equals to half, the characteristic function defined on this omega, it does not belongs to, it does belongs to H0 half, but it does not belongs to H half tilde. And for, in particular, for half, you also know there is another space that's called this Lyon's Megan space, probably that's H half 0, 0, because, and those spaces are defined through that the distance functions from the distance function from a point inside the domain to the boundary. And whether, it's kind of checking the Hardy inequality every time, in certain sense, that whether u divided by the distance function to the power a is less than infinity or not. And if it is, then it belongs to that space, that in particular this Lyon space, that H1200. So you get a lot of different versions of this fractional symbol spaces just to tackle the.
So Tuhin, sorry to
Yes,
interrupt.
sorry.
So it's actually past 7, and there are two questions. So maybe you can continue
Sure.
after the break. But there are two
Wow.
questions over here. So
It's in the chat.
so one question is, I'll read the smaller question, the smaller question first. Are you working with real valued functions? So this is from Philip Zimmerman.
Yeah, so you can, I mean, it's all linear equations. So you can, it doesn't really matter that whether you are considering the real valued functions or the complex valued functions. Essentially, for instance, that in the previous lecture, what you have seen that that they are considering the complex geometric optic solutions. The complex geometric optic solutions are essentially that complex valued functions. But even the DN map is given for the real valued functions. You can always do this F1 plus IF2 thing. You can go from real value to the complex valued functions. You can extend the DN map and so on and so forth. So, so I think that you can do it in either way. So it's kind of okay. The next questions are.
So there is one more question from Murali Reddy. So can we think sub or super diffusion problem as a stochastic PDE? Or can
Yeah,
you
exactly.
transform
Yeah.
the fractional PDEs into a stochastic PDE having randomness in either coefficients, source term, or in the initial or boundary conditions?
Well, I can't guarantee for, but definitely this is one of the example, and he's right that you can consider with source term or the boundary conditions means like not the boundary condition, probably the exterior conditions. The boundary conditions are there that is defined via the something called this Hormander mu transformation. It's a little complicated because you need to take care of this the distance functions to the point to boundary. But yes, I mean, in certain sense, you can consider those diffusion process with certain boundary conditions or sorts terms and so on. So, and it's kind of this, yeah, and it leads to stochastic differential equation. Yeah, so you can say that yes, true.
So, so thanks to him, and then
it is true that they also try to recover or try to recover the coefficients or like or whether it's possible to recover such coefficients. Yeah.